Hey everybody, Dr. A here, and in this video we are going to be exploring a steel beam column check example. So we're going to be referencing the AISC Steel Manual, the Big Steel Manual 15th edition, so you want to go ahead and have that out and ready to use along with me. And I'm also going to be using my TI-36X Pro calculator, so go ahead and get your calculator out with us as well. So let's look at our given information. A W12 by 65 A572 grade 50 steel member is part of a braced frame. Okay, so a couple things to take away from that. Grade 50 steel means that your yield strength is 50 ksi, right? F sub y is 50 ksi. Braced frame is the context clue that you're going to be dealing with P little delta effects, and thus you're going to be dealing with a moment magnification factor B1, okay? You will not be dealing with P capital delta effects because, again, we have a braced frame. So you got to take these context clues, okay, in the directions. We're then told that flexural bending is about the strong axis. Again, context clue there is that flexural bending is about the cross-section XX axis, okay? We're told that the effective length factors for buckling about the X and Y axes are both 1.0, and that's indicated in the figure by these little open circles at the top and the bottom of the member. And then we're being told to determine if the member is adequate and to use LRFD. All right, so let's take a look at our figure here. We have this 14-foot long member that's part of a braced frame, and it's sustaining axial compressive dead and live loads here at the top and the bottom. You see this axial compressive force at the top and the bottom. The dead load is 70 kips, the live load is 200 kips. Now, it's also sustaining a dead and live load moment at the top connection and the bottom connection that are different from one another. So the dead load and live load moments here at the top are 10 kip feet and 35 kip feet respectively, and at the bottom they are 15 and 40 kip feet respectively. Now you may be wondering, well, this is not an equilibrium. Well, remember, this is an isolated member that's pulled out of a larger braced frame system, so we can assume that the entire frame is in equilibrium by analysis, and these are just the results of our analysis. Okay, so these are dead and live load results of a more complex frame analysis that maybe you use some software to perform, or you explored that by hand using some structural analysis techniques. But we're not really concerned with that. We're just concerned with what's going on with this isolated member. Okay, so let's go ahead and get started. We're going to write solution here, and the first thing we're going to do is compute the LRFD factored loads. Okay, and so if you remember from LRFD, you have load combination 1 is U equals 1.4 times the dead load, and load combination 2 is U is 1.2 dead load plus 1.6 live load. So we need to really quickly check both of these for the axial compressive load and both sets of moments. Okay, so let's go ahead and write this out. We're going to say PU equals, and we can say 1.4 P dead, and then we can say check the PU equals 1.2 P dead plus 1.6 P live. So I'm going to punch both of these in my calculator quickly and see what we get. So 1.4 times 70 is 98 kips, and then we have 1.2 times 70 plus 1.6 times 200. You probably could have guessed that second combination is going to be the one that governs, because that live load is so much bigger than the dead load. So this is going to govern for our PU, 404 kips in compression. Okay, now similarly we need to investigate the top and the bottom moment. So let's call this MU top, and we're going to say that that's 1.4 M dead top, and we're going to see what that comes out to be. 1.4 times that dead load moment at the top was 10, so of course that gives us 14 kip feet. And then we can also check MU top with the second load combination, 1.2 M dead top plus 1.6 M live top. And again, right now we're only checking the top moment. So 1.2 times 10 plus 1.6 times 35, and I get 68 kip feet. 68 kip feet, and that is going to be the governing moment at the top. And then similarly, we need to get the factored moments at the bottom. So MU, we'll call this bot, is 1.4 M dead bot. And then we'll get MU, check the second load combination, MU bot is 1.2 M dead bot plus 1.6 M live bot. And let's see what those come out to be. So we have 1.4 times 15 is 21 kip feet. And then checking the second load combination, 1.2 times 15 plus 1.6 times 40 is 82 kip feet. Now, you may be savvy enough to where you can just look at these magnitudes and you can automatically tell, since the live load is so much bigger than the dead load, load combo 2 was going to govern on all of these. That's fine, but when in doubt, it's a good habit to check, all the applicable load combinations. Okay, so let's keep moving. We have MU, the MU values at the top and the bottom. Let's go ahead and sketch out the moment diagram just to have it, okay? So I'm going to say let's sketch, see if I can spell sketch right, sketch the moment diagram for the member, okay? And you're going to see that this is going to be helpful to us later on in one of our later steps. So here is our member, and it's 14 feet long, and we have single curvature, right? You can look at the moments acting on here. You see that the moments at the top and the bottom are actually going in opposite directions relative to each other, which means that we have single curvature bending, okay? So that means this thing will bend, with one type of curve like that. So let's go ahead and sketch this moment diagram. That means the moment diagram is going to be all on one side of our axis. It's all going to be, you can think of it as all either positive or either negative. So our moment diagram is going to increase up to 68 kip feet, right? That's this top moment right here. And then it's going to linearly increase up to 82 kip feet. Let's draw that a little bit better. Linear increase. Again, I don't have very good sketching skills. This is going to be 82 kip feet, okay? And so this is our moment diagram, and you can shade this in if you really wanted to. Now, how do you know it's linear? This is linear right here. So think back to your knowledge of analysis. That's linear because you have no other loads applied along the axis of the member. You just have these couple moments at either end. So that means that you're not going to have anything acting transversely on the member that's going to cause this moment diagram to be any other shape except for linear, okay? Now here's the next question. Which one of these is going to be eventually what we call M1 and M2? Well, if you remember from our background information on the moment amplification method, M2 will always be the larger magnitude moment, okay? So this 82 kip feet will be our M2, and then the 68 kip feet will be our M1. I'm going ahead and I'm labeling these right now. This is going to be useful later, again, once we get to our moment amplification process, okay? So these are our LRFD factored, requirements. Let's go ahead and get the strengths now. So let's reference AISC 15th edition, right? Steel Manual, Chapter 6 or Part 6, okay, on combined loading, all right? And so what I'm going to do is I'm going to enter table 6-2. So go ahead, open up your Steel Manual, and I'll make your life easier. In the 15th edition in table 6.2, I am on page 6-87, okay? 6-87. So if you notice, you know you're at the right table because F sub y is 50 KSI. That clearly says that at the top of table 6.2 on page 6-87, okay? And so if you look in that kind of middle column of your steel manual, it says effective length LC with respect to least radius gyration or unbraced length with respect to XX axis bending. So let's look at the right side of the table first, okay? The right side of the table will give us our phi b mn values. So I'm going to go to a 14-foot length, and for 14 feet, I'm going to read off a phi b mn as 345 kip feet, okay? So we're going to say phi b mnx is 345 kip feet for an unbraced length of 14 feet, okay? So now this is based on, remember, this is based on a CB factor equaling 1.0, all right? Now, if you notice, we have non-uniform bending and, again, single curvature, so we need to calculate our CB factor. So we must compute our CB factor, that's that moment gradient factor due to non-uniform bending moment. Let's see if I can spell bending correctly. Okay, so the way we do that, if you look in your steel manual, you don't actually have a case for a ready-made case for this type of shape. So what you're going to do is use the governing equation, CB equals, and that's going to be 12.5 M max all divided by 2.5 M max plus 3MA plus 4MB plus 3MC, okay? Now, remember, MA, MB, and MC are the moments at the quarter points on your moment diagram. So if we look at this moment diagram, I'm just going to go ahead and use this moment diagram to kind of help me identify these quarter points. So we'll have quarter points right about at these points. This will be A, B, and C, and of course this is 3.5 feet, 3.5 feet, 3.5 feet, 3.5 feet. So what you're looking for is MA here, you're looking for MB here, and you're looking for MC here. Now you can find the slope of this line or use some form of linear interpolation. But if you notice, just make your life easier. This is linear, right? And these points A, B, and C are quarter points. So you can easily just kind of look at this and just take a couple of averages and you'll be in good shape. So watch this. I'm going to say MB is the average of M1 and M2. Now, I'm only able to do this because this is linear here. If this was a nonlinear moment diagram, I couldn't just do that. But this is linear, so I can use regular arithmetic averages. So if I average 68 and 82, I get MB is 75 kip feet, okay? And then similarly, I can get MA as the average of MB with 68, okay? So I can say 75 plus 68 over 2, and that's 71.5 kip feet. And then MC would be the average of 82 and 75, and that's 78.5 kip feet. And again, I want to emphasize I'm only able to do that because this moment diagram is linear. If you had any other shape, you could not just take simple averages or use like this midpoint averaging mechanism, okay? So let's go ahead and calculate CB, and I'm going to pull my calculator out and try to do this right the first time. So M max, remember, is the 82 kip feet, right? So let's punch this in our calculators together. I'm punching along right with you guys. And I'm already making a boo-boo in my calculator, but that's okay, I fixed it. 4 times MB is 75, plus 3 times MC is 78.5. Okay, and then 12.5 times 82, and we divide this. So I get a CB factor of 1.07. Okay, so punch that through, make sure you get the same thing as me, but I get 1.07. So now what you can do is you can say CB times phi B MNX, and we can ramp up, we can squeeze a little bit more strength out of that 345. So we'll say 345 times 1.07, and that gets me to 369.2 kip feet. Now remember, you are bounded by your plastic moment. Okay, so this must be less than or equal to phi B MP, and so phi B MP is going to be equal to 356 kip feet, and I'm obtaining this from the same table 6.2, for an unbraced length of 0. Okay, so we're gonna use phi B MP equals 356 kip feet as our flexural strength. Okay, so so that's our flexural strength. Now from the same table 6.2, we need to get our axial compressive strength. Okay, so I'm still on that same page in my steel manual, again for a length unbraced, or a effective length of 14 feet. My phi CPN, same table, but on the left side of the table, is going to be 685 kips. Okay, so make sure you see where we are in this table. The next thing we need to do is investigate which interaction equation we need to use. So let's make a note: which interaction equation is applicable. So if you remember, the way we do this is we compute PU over phi CPN, okay? And we compare that to a value of 0.2. So let's do that. Our PU value, if we scroll on up, what was PU? Already forgot it. It's all the way at the top. 404 kips, okay? So that's 404 kips divided by that strength, 685 kips, and let's see what that is, 685. Okay, that's 0.59, which is clearly bigger than 0.2. Okay, so that's going to tell us which interaction equation we should be using. So let's flip back maybe in our notes. Don't feel bad, I'm flipping back in my notes too. I don't have any of those equations directly memorized. So when this is larger than 0.2, we're going to use the following. We're going to say use PU over phi CPN plus 8/9 times MUX over phi B MNX. And, you know, if you want to write this in biaxial form, that's plus MUY over phi B MNY. And, you know, we know that this whole term is 0 because we just have uniaxial bending, and that must be less than or equal to 1.0. All right. So looking at this equation, this is the general equation. Now we also need to apply our B1 factor to MUX. So if you look right here at this MUX, again, we're going to use the moment magnification method. So let's go ahead and be very clear on that. We're going to have a B1 times MUX, in that numerator, okay, due to our moment magnification process. So what do we do next? Well, we're almost there, okay? We're about ready to move forward. So B1, that moment magnification or amplification factor, is equal to Cm all divided by 1 minus alpha Pu over P Euler, okay? And remember that Cm is equal to 0.6 minus 0.4 times M1 over M2 when you have single curvature bending and you don't have any transverse loading, okay? Now, with single curvature bending, you need to embed a negative sign into this ratio. Why is that? Well, I think of it as your M1 and M2 are acting in opposite directions of one another. So this ratio needs to be negative because one of these moments will have a sign change compared to the other one of these moments, okay? So our Cm factor is going to be 0.6 minus 0.4 times negative, and then M1 going back up here, M1 is the smaller absolute value, so we have 68 kip feet, and then divided by 82 kip feet. 68 kip feet divided by 82 kip feet. And so punch this in your calculator, make sure you get the same thing I get, but I am getting let's see, 0.932. There we go. 0.932. Make sure you get the same thing as me, okay? Alpha is 1.0 for LRFD. We know that from before, one of our previous videos. Now we need P Euler. P Euler is the Euler buckling, force, but about the axis of bending, okay? So this is pi squared E times I sub x all over KL squared, okay? Now again, this is I sub x because we have x-axis bending, okay? X-axis flexure, okay? That's why we have I sub x there, so be very careful. So we can go to the part 1 of the steel manual and get I sub x. So we have pi squared times 29,000 KSI times 533 inches to the 4th all over. Now be very careful here. We've got 1 times 14 feet times 12 inches per foot squared, okay? And let's see what we end up getting. I already punched this through, but I always like to check myself. So I'm getting 5,400 kips as my P Euler. Make sure you punch that in your calculator and you get the same thing I'm getting. And so let's go ahead and calculate this B1 factor using our governing equation. Cm is 0.932 all divided by 1 minus 1 times, what was our PU again? I think it was 404 kips if I remember correctly. 404 kips divided by P Euler, 5,400 kips. And let's see what we turn up here. 404 over 5,400, 1 minus that value, and then 0.932 divided by that value. So I get a pretty small number, but 1.007. So again, this is bigger than 1.0, so we're going to use it. And so here we go. We're going to enter into our interaction equation, and we're going to say, let's color coordinate here. We got P, I like to rewrite my equations, as you can tell, PU over phi C P N plus 8/9 times B1 MUX over phi B MN. Must be less than or equal to 1.0, okay? And let's go in one at a time. We already know PU over phi CPN, right? We calculated that earlier as this 0.59, so we can just go ahead and utilize that. That's 0.59 plus 8/9 times 1.007 times MUX. So what is MUX? Well, that's going to be the largest of these M1 or M2 values. So that's going to be our 82 kip feet. Okay, so we're going to come in here times 82 kip feet, and then we're going to divide that by our 356 kip feet. That's our Phoebe MP, the factored plastic moment. And then let's see what this comes out to be. 1.07 times 82 divided by 356 times 8/9 plus 0.59. So I'm getting 0.796, which is less than or equal to 0.1. So finally, the W12 by 65 member is adequate for the loading. Okay, so if you think about it, was this hard? Not really difficult, but you are kind of chasing down a lot of numbers and, substituting in a lot of values into governing equations. So you got to be careful. Be very careful with your calculations. But that is the conclusion of this example. I hope you liked it. Please hit like and subscribe.